Hi, today I'm going to talk about the solutions for Atcoder Beginner Contest 409 problems A to F. And for this problem, there are n items and then we are given two strings T and A that represents which items Takahashi and LQ want. And a circle represents that they want the item and an X represents that they don't want the item. And we want to find whether there is an item that both of them want. So we can directly loop through the two strings and see if there's a position that both have circles in these strings. And if so, we can print out yes. Otherwise, we output no. And let's look at the code. So I first input these strings, and then I loop through the two strings to check if there's a position that has a circle in both of these strings. And if so, we can output yes and stop the loop. Otherwise, at the end, we can output no. Next, let's look at problem B. For this problem, we have a sequence of integers a, and then we want to find the maximum non-negative integer that has at least x items in A that are greater than or equal to x. And so for this problem, we want to find the maximum non-negative integer, and to do this we can use binary search. And we can first sort the array A and sort it in increasing order. Then we can binary search on the value x to find the maximum position that satisfies this constraint. And so for this problem, for sample input 1, the value 1 is the greatest x that satisfies the condition, because if the value is 2, then there's only one number in A that is greater than or equal to 2, which is 2 itself. So it doesn't satisfy the condition, but then if the number is 1, then there are 3 numbers that are greater than or equal to 1. So the maximum x is equal to 1. And now let's look at the code. So I first inputted all the values for A, and then I sorted them in increasing order so that we can do binary search on the array. Afterwards, this part is the binary search for x, and L is the minimum value, which is 0, because x needs to be a non-negative integer, and if the value is 0, then this is guaranteed that there will be a solution. And since all the numbers are in the range of 10 to the power of 9, R would be set to the maximum value, which is 10 to the power of 9. And this part is the binary search, and we can use lower bound to compute the number of integers in A that are greater than or equal to our current value of x. And if it is, this part we can change if it is, we can move L to mid plus 1, and otherwise we can move R to mid. And in the end, we can output L minus 1, because this part we set L to mid plus 1, so it represents the smallest number that is not possible. And so if we subtract that by 1, then that's the maximum number of x that we want. Next, let's look at problem C. For problem C, we have a circle of circumference L, and then there's n points on the circle. And for these points I plus 1 is located at a position that's di clockwise from point I. And we want to find the number of triples that has the 3 points are all distinct, and the triangle formed with these 3 points is an equilateral triangle. For this problem, we know that an equilateral triangle will split the circle evenly by 3, and so these things will all be equal. And then so we can count the number of points that have position plus the circumference divided by 3, and position plus 2 times the circumference divided by 3. And so we can first, from the input given, we can compute the position for all the n points, and then we can sort them by increasing order. Then we can use lower bound and upper bound to compute the number of points that have this number and the points that have this number. And afterwards, we can multiply the counts together to find the number of triples that satisfies this condition. And if the circumference is not divisible by 3, then that means that it's not possible to create an equilateral triangle because there's no points that will evenly split the circle. And let's look at the code next. So this part, after the input, I first checked if the circumference is divisible by 3. And if not, I just output 0 because it's impossible to have a triple that will satisfy the constraints. And afterwards, I inputted all the values for D, and I calculate the positions based on the conditions in the problem, which is position I plus 1 is equal to the previous position of I plus di. And I took the remainder of this position divided by the circumference, because if we calculate it by this, it would exceed the value of the circumference. And afterwards, I sort the positions in increasing order, so we can use lower bound and upper bound since it's sorted in order. Afterwards, the distance is the circumference divided by 3, which is the distance we want between our 2 points. And I loop through the points so that we can count the number of triples that satisfy the constraints when the smallest point is our current point I. So the first point in our triple will be I, and then we count how many combinations of the next 2 points can allow us to create that triple. And so we want to find all the values that have position equal to the position of I plus L divided by 3. And so we can do this by finding the lower bound and the upper bound of this value, because lower bound finds the number that is greater than or equal to this value, and the upper bound finds the index that is greater than our desired value. So if we find lower bound and upper bound, and use j2 minus j, then we get the count of the number of points that have position I plus L divided by 3. And we can do this for the other point as well, which is our third point in the triple that we want is position plus 2 times distance. And we do the same thing. In the end, we multiply these together because then we have the number of triples for when the first number in the triple is point I. And after we loop through all the points, we have our answer. And if j is equal to k, then that means that no future points are possible because we want our triple to be sorted in order. Otherwise we will overcount. So the values in our triple always need to be increasing. So if j is already equal to k, then that means that there is no triples that can work if I is greater. For problem D, we have a string of length n that has lowercase English letters, and we can perform one operation, which is we can choose the one contiguous substring and shift the substring to the left by 1. And we want to find the lexicographically smallest string that we can have after this one operation. And so, for example, for the sample input 1 for Atcoder, then we can shift the 2nd to 7th character and shift it to the left and then move T to the end, and we have this string. Then this is the smallest string that we can have given this one operation. Since we can only perform exactly one operation, then we can swap the first position that has Si greater than Si plus 1. And this is because we want to find the lexicographically smallest string. And we check lexicographical order from the first character of the string all the way to the last. And so if one character is already greater, then the string would be greater than some other string, even if characters at the end are smaller. So we compare characters from the first one to the last one, and then find the first character that's different, then compare which one is greater. So we want the front positions to be as small as possible. So when we see the first position that has Si greater than Si plus 1, we can perform the operation on L equals to I and R equals to some other value. And then, so that way we can move this position to here, and that position will go to the back. And this would make the string smaller. And so to find the R value, we will want the operation to include all characters that are smaller than Si. So that way we will move all these characters in front of Si, and then that would make our string the smallest. And for example, in the string Atcoder, when we see that T is greater than C, we know that L can start from here, 1. And then afterwards, since all the characters in this range are smaller than t, r can go all the way till here. I think this is 6. Okay. Yeah, and so we would shift all the numbers C, O, D, R to the front, and then T would go to the back. And this would give us this. And now let's look at the code. So there are T test cases, and I first inputted the N and S. Afterwards, I set K equals -1, which is to check if the string is already in the smallest order possible. And we loop through the string to check if there's an index that Sj is greater than Sj plus 1. And if it is, our L would start at this location. Then K is first equal to N, which represents that, which is an initial value, and then we can check when we should stop the operation. And I used K to represent the R value of the operation. And then, so we can loop from L and then check all the way until some value X in the string is greater than the character at position L. And that means that we would stop our operation there. Then K would equal to X, which is the location of the end of our operation. And then if K is still -1, then this means that the if statement did not run and the string is already in the smallest order. So we would output that string. And otherwise, we would output the characters from the first one to L, and then from L plus 1 to K, because the character at L would go to the back of the operation. And after we output this, we output L, and that way this region is cyclically shifted. And afterwards, we output the end of the array. For problem E, we have a tree of n vertices, and each edge bidirectionally collects the vertices u and v and has a weight of j. And each vertex has an integer of xi, and if xi is greater than 0, then this means that xi positrons are placed at vertex I. Otherwise, it means that negative xi electrons are placed at that vertex. And if we move one particle along edge j, it would cost an energy of j. And when a positron meets an electron, then they annihilate each other. And we want to find the minimum energy required to annihilate all positrons and electrons. And because this is a tree, we realize that all the points from the leaf will have to move up to the root. So the minimum path for all the positions would be to move up to the end. And so we can perform a DFS on this tree and keep track of the xi at each position after all the particles in the subtree moved up to that node. And if so, for example, here there will be some electrons and here some positrons, and then they will all move up here, and then some number will annihilate here, and then we will use xi to keep track of the remaining particles that are here. And then these will continue to do the same, which is to move up at the end. So the particles will all move from the leaves up, and then they would disappear. Some of the particles will disappear at these nodes, and then the rest will continue to move up and then disappear. And so we can keep track of the xi at each position after all particles in its subtree have moved up. And afterwards, we can also keep track of a cost variable which will store all the costs of moving these particles up. Next, let's look at the code. Here I first inputted all the points, and then I stored the graph in a vector of pairs with the index matching to the destination. So the first part of the pair will store the destination node of this edge, and the second part of this pair will store the weight. For the DFS, we can, since this is a tree, we can check if the next node is equal to the parent. So if it's not equal to the parent, then we can continue to DFS. And the cost here is to keep track of the cost to move all the particles up. And here, after the DFS, we can add all of the particles in this edge to the parent node, and this means that we can move the particles here in the V node up to U node. The cost of this operation, since we need to move all the particles up, will be the absolute value of xv, which is the number of particles multiplied by the weight of the edge, which is the cost. Since the two particles are represented, one as a positive number and one as a negative number, if we add these together, this will represent the resulting number of particles that we have at location U after all the particles in its subtree has cancelled out. And this will continue to move up towards the root. So after we perform the DFS, the cost variable will store the cost of moving all the particles upwards towards the root as they cancel each other out in the process. Lastly, we have problem F. And problem F, there's a graph of n vertices, and each vertex has coordinates x and y. And the distance between 2 points u and v is defined by the Manhattan distance. And we need to process Q queries. Each query can be one of three types. The first one is we would add another vertex n plus 1 into our graph, and the vertex will have the position A, B. The second type is that we want to merge all the components with the minimum distance together and output the value of the minimum distance. And if we can't merge any components, we output -1. For the third type, we check if the two vertices u and v are in the same component. If so, we output yes, otherwise we output no. Let's look at a sample input. In sample input 1, the points initially look like this. We have the floor points, each at positions written here. And next, we process the queries. The first query is of type 3, where we check whether the vertexes 1 and 2 are in the same component. Since these are all in separate components at the beginning, so we will output no for the first query because these two vertices are not in the same component. Next, we have a query of type 2. For type 2, we connect the components that have the minimum distance between them. In this case, the components that have a minimum distance is vertices 1 and 2. So we connect them together. And next we have another operation, which is checking if these two vertices are in the same component. Oh, and I forgot. For type 2 operations, we need to output the minimum distance that we have, which is the distance between vertices 1 and 2 when we connected them together is 1, so we output 1. Next, since these vertices are connected, then we output yes. Next, we have the operation of type 1 to add a point numbered 5 located at 6, 4. And we do the following for the rest of the queries. And now let's look at how to solve this problem. Since we want to keep track of connected components and quickly unite two components together, we can use a disjoint set. And we want to keep track of the edges, the minimum edges for the type 2 query. Then we can use a priority queue to keep track of all the edges. Because if we use an array, we will need to sort the array, and every time we need to loop from the beginning of the array, and this would take too much time. So we can directly use a priority queue to store the edges. Then we can add edges, unite the components from the front of the queue. So initially, we have some number of points. So we first compute all the distances between the points and then store it in the priority queue. And this is acceptable because the n can only be at most 1,500. So a n squared solution would be fine. Then for type 1 queries, we add the new point and add edges between all the previous points that we have and our current point into the queue. So we compute the distance between all the previous points and the new point that we added and push it into the priority queue. For type 2, we can merge the smallest edges that are popped from the front of the priority queue, and we can check if the points are already in the same component. So if they're not in the same component, we can unite the points. We would unite all the points that have the same minimum distance. So we can unite multiple components if they all have the minimum distance between them. Then for type 3 queries, we just directly check if the points are in the same component with using the disjoint set. Now let's look at the code. Here I first inputted all the positions of the initial vertices, and this part I computed the distance between all the vertices. So all possible distances between the existing vertices are pushed into the priority queue, which stores I defined a struct of E, because that way we can store the initial point, and then that way we can store the edge with the starting point and ending point, and also the weight of the edge. And we can also use a custom comparator to allow us to use a priority queue and sort the edges from the minimum weight to the maximum weight. So that way the priority queue would have edges with the minimum weight at the front. This part we process our queries, and for type 1 queries, we input the values, then we find the edges that we have between the new node and all the previous points that we have, and we push this into the priority queue. For type 2 queries, k is initially -1, then we loop through our priority queue, and we pop an edge from the front of the queue. If k is not equal to -1, then that means that we've already found an edge with the minimum weight. Then that means that if our current edge is not equal to k, then we won't unite the component because it's already not the minimum edge. Then we break out of this loop because we will we will unite no other components since the other edges all have a value of greater than k. And otherwise, if the weight is still equal to k and the 2 points are in different components, then we unite the 2 points into the same component. And k is set here when we have an edge that has vertices in different components. Then we set k equals to the weight of this edge. This happens when k is still -1, which means that we haven't found a valid edge yet. And if so, this means that we found one, and then we will set k equals to this edge weight, and we will unite these vertices. So this loop allows us to unite all the components with the minimum edge. Then in the end, we output k, and k will be the minimum edge that we have, or -1 if we didn't unite any components. Then for a type 3 query, we directly check if the disjoint set, using the disjoint set to check if vertices u and v are in the same component, and output the answer accordingly. And D is the disjoint set, which is written above here, and position is represented in pairs of integers. And thanks for listening.